Hey y'all, today's lesson is going to be about optimization. Optimization is all about maximizing things or about minimizing things. And I know that we've done that before, but here the difference is going to be the things you're maximizing and that you're minimizing are one, more interesting than they've been in the past, and two, the function that you need to use to maximize or to minimize is something that you are going to build. I've put up a problem set. There's 12 questions on it. I'm going to work every single one of them out below. Okay, have fun. It's problem number one, and here's what's going on. I want you to imagine that we have a road. That road is a curvy road. And the equation for that road is y is equal to e to the x. And I also want you to imagine that you are not on the road. This is you. You are sitting at the point 0, 0. And you're going to walk to the road, and let's imagine that it's incredibly muddy outside. And so you want to walk the shortest possible path to the road. Well, there's a couple different ways that you can approach this, but one of them is to build an equation for the distance from 0, 0 to any point on the road. And that's what I'm going to do. Now, just a reminder from back in your geometry days, if you have 2 points and you're looking to find the linear distance between them, what you do is you think about the linear distance as being the hypotenuse of a right triangle, where one leg is the change in x and the other leg is the change in y. So this distance is not unlike this distance down here. And therefore, we can say that the distance is equal to the square root of the change in x squared plus the change in y squared. Notice that all I'm doing is applying the Pythagorean theorem. I went ahead and rather than saying d squared equals blah, 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 I just square rooted both sides. We got it set up this way. All right. Now, what we would like to do is rewrite change in x and change in y in terms of the information that we know. So from x to 0, that would be x minus 0, the quantity squared. And then from y to 0, that would be the quantity y is e to the x minus 0, the quantity squared. So the distance, I'm going to simplify this a little bit, is really, boom, boom, x squared plus e to the x squared would be e to the 2x all to the half power. Last thing is you want to think about what the possible values of x are. In this case, x could really be anything. It could be way over here down to negative infinity or all the way up here to positive infinity. Okay, so think of all of that so far as stage one. What we did is we, one, drew a picture. Two, we wrote an equation for the thing that we are trying to optimize. By optimize, I mean that we want the optimal value of this distance right here. We want it to be at a minimum. And then finally, the third thing that we did is we took that equation and we rewrote it so that the distance is entirely in terms of a single variable. And that variable is x. So we could write this as d of x. So again, that's stage one. Here's what stage two looks like. So in stage two, what we're going to do, since we want the minimum, is we are going to first take the derivative of our equation. So the derivative of this equation using the chain rule would be 1/2 of the inner function to the negative 1/2 power multiplied by the derivative of the inside function, which is 2x plus 2e to the 2x. All right. Now we want to know the places where that is equal to 0. The reason we want to know where this is 0 is you can imagine, you can kind of picture it here that, if you start way over here, if you start with a point that's way over here, that distance is going to be very large. And then as we move from there to there to there to there to there, see that those distances are going to be getting smaller. And they're going to keep getting smaller until somewhere around here. And then they're going to start getting bigger again. So if you think about this distance equation, it's like smaller, 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 minimum, bigger, 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 bigger. And we know that at that minimum, the rate of change will be 0. So that's why we're taking this rate of change equation. We're setting it equal to 0. I'm going to clean this up a little bit. You see that this half right here will actually cancel with these two. And we end up with x plus e to the 2x divided by the square root of x squared plus e to the 2x. So we now need to figure out when this is 0. And we know that this will be 0 when x plus e to the 2x is 0. The denominator is always going to be positive. At this point, this is an equation that you can't solve using algebra, so you're going to have to use your calculator. So I've plugged x plus e to the 2x into my calculator, and I'm looking for where it's 0, so I want to know where this crosses the x-axis. I know from looking at the picture up here that it seems like the minimum of the distance is going to happen somewhere where x is slightly negative, right here. So that means the 0 of this should happen at a place that is slightly negative. So when I pick my window, I'm going to say maybe from like -2 to 2, and then I'm going to do a zoom, and I'm going to come down to fit. I'm going to let it graph. And sure enough, I've got a 0 somewhere around here. So let's go calc. Let's see, 0, number 2. And I know that that's a left bound, and there's a right bound, and I get x is equal to negative 0.426. Now the last thing is we want to make sure that we answer the question. If you look at problem number 1, it actually asks you what is the location of the point that is closest. So what we need to do is give the x value and the y value. The y value would be, let's see, we're on e to the x. So e to the negative 0.426 gives us 0.653. That's the location we should be walking to. And there's our first example. Now, the last thing I want to do with this is I want to point out that in stage 2, there were 3 steps that we went through. The big one right here is finding the critical points. And we did that by taking the derivative and then setting it equal to 0. So we took the derivative. We used it to identify the critical points. And then the third and final thing on this one is that we made sure that we answered the question that was asked. There's one thing we didn't have to do in this case, and that's that we did not have to check the endpoints. Remember that maxima and minima can happen at endpoints. There's a good reason that we didn't have to do that in this case, and it's that it didn't make any sense. Back here, when I looked at what the possible values of x are, notice that it went from negative infinity to positive infinity. So there were no endpoints for us to check. I'm going to do number 2 in 2 different ways. The first way is going to require no calculus at all. Same setup as the last problem. we've got a point, and we want to walk from that point to a road, which is defined by an equation. But the equation this time is y equals x, and the point is 1, 0. And so we know, just because we know a little bit about how geometry works, that this has to be a right angle. It was true in the last one too. And because this has to be a right angle, these distances end up being equal, and these end up being 45 degrees. Now, if that's the case, that means that this point right here is going to be a bisector of the segment from 0, 0 to 1, 0, which means that this point right here, we know right away needs to be 1/2. And if x is 1/2, then y also has to be 1/2. So there's the answer to the problem. Now I want to show you how we could do this same problem using optimization. So we'd start by saying the distance is the same formula as last time. But this time around, things are going to look a little bit different. Okay, maybe I need a different color. Let's do this. Okay, so I'm going to pick some random point here. Let's call it x, comma, y. And I'm charting the distance from here to here. And the distance for x would be the difference between x and 1. Right? It's like, how far apart are those? So this would be x minus 1, the quantity squared. And then the distance from y would be y minus 0. So that would be y minus 0 squared. But isn't y just the same as x, because this is y equals x? So I'm going to go x minus 0 squared. And then I am going to go ahead and simplify this a little bit. So this is x squared minus 2x plus 1, and that's another x squared. So it's going to be 2x squared minus 2x plus 1 to the 1/2 power. So this simplifies to this. Once again, x can be anything in this problem, negative infinity to infinity. So that was the end of stage 1. In stage 2, first thing we need to do is take the derivative. So I'm taking the derivative of this character right here. I get 1/2 2x squared minus 2x plus 1, all to the negative half power, multiplied by the derivative of the inside function, which would be 4x minus 2. Now the next thing we need to do is we need to set that equal to 0. Notice that this 1/2 is going to cancel with the, actually, you know what? I think I'll just leave it this time. So we're going to get 4x minus 2 in the numerator. On bottom, we're going to get 2, that's coming from here, times the square root of this jazz. And to find our minima, we want to set this equal to 0. So 4x minus 2 would be 0, means that x would be equal to 1/2, which brings us to our point is 1/2, 1/2, which is exactly the way we found it using the geometric method. Good stuff. On to number 3, one thing that I think is kind of helpful on these problems is rather than labeling your point as x comma y, call it x comma whatever y is in terms of x. Because if you do it that way, then you can pretty quickly get to this stage in the game where you say the distance is equal to the square root of, let's see, from here to here would be x minus 1 squared, plus from here to here would be x squared minus 0 squared. And that's going to simplify to x to the 4th, I got that from this term, plus, do I want to clean that up? Yeah, I'll call that x squared minus 2x plus 1. I probably didn't have to do that. Just like the last bunch of them, x can be anything. The world is its stage. Speaking of stages, that's the end of stage 1. Let's go to stage 2. In stage 2, you're going to take Mr. Derivative for this guy, which will be 1/2 all of this chunk to the negative half multiplied by 4x cubed plus 2x minus 2. So what we're really setting equal to 0, I'm going to move a little bit faster, is just this chunk right here, because you know that this is going to move to the denominator like it did before. So we want to know when this is 0. And I don't really know any easy way to do this algebraically, and I have a calculator in my hand. So let's put it to use. So I put the equation into my calculator, and I know that I'm trying to minimize the distance. The distance looks like it's going to be the smallest to me, somewhere around here. So x is going to be somewhere between 0 and 1. So that means that here, for the window, I'm going to go from 0 to 1, and then I'm going to do a zoom fit. And sure enough, there it is. Let's do calc 0, left bound, right bound. I've got the answer now. Let's see, x is 0.5897. We'll call that 0.590. And the question, what is this question asking us for? It is asking us to determine the point. Okay, so all we need to do is put in x is this, and y will be the square of that number. Well, .438. I'll go 3 decimal places on this one too. There's our answer. Hey, we are up to number 4, and number 4 is a little bit trickier, so make sure you really pay careful attention to this one. Number 4 says we got these two functions. We've got 0.8x squared, and we've got sine of pi x. And we want to find the maximum vertical distance between them on the interval from 0 to 1. So here's what I did. I put the equations into my calculator, and then I go to window, and under window, I went from 0 to 1, so I could just see that range. And then I did a zoom fit, and the graph looks something like this. I drew a picture over here. Now, here's the thing. What I see is that there's kind of two possibilities for where the distance is at a maximum. It could be that, I don't know, vertical distance. These vertical distances look like they're getting bigger until somewhere around here, and then they start to get smaller again, and they get to be 0. Now, when we get over here, they start to get bigger again until right here at 1. They're pretty darn big. So the question is the biggest vertical distance going to be here at 1 at the end point, or is it going to be at one of these values somewhere in the middle? So that's the big idea. Now what we need to do is we need to write an equation for the distance. Now on this region right here, the sine curve is bigger, but over here the quadratic is bigger. So the way I'm going to fix that is I'm going to say that the distance is the absolute value of g of x minus f of x. And on this one, I am bounded for what x can be. X can be at most 1 and at least 0. And there is stage 1 of our problem. Stage 2 is going to look like this. I have to take the derivative, and the derivative would just be the derivative of g minus the derivative of f. I'm not worrying about the absolute value for the moment. So let's see. We want to know when this is 0. The derivative of g would be pi times the cosine of pi x minus the derivative of f would be 1.6x. So we want to know when this quantity right here is 0. To me, it looks like it's going to happen somewhere kind of close to the middle of the interval, somewhere close to a half. Same issue we've been dealing with. This is an equation that can't be solved using algebra, so we're going to have to use our calculator. So my window goes from 0 to 1, just like it did before, and I'm going to do a zoom fit. And that 0 is close to a half. Not at a half, but close to a half, just like I had suggested. So that 0 is going to be at 0.430. So we're in the home stretch here, and this one is different than the last couple of problems because we have to check the endpoints this time. So this was our critical point. You gonna focus? You're just gonna keep going out. Our critical point was 0.430, 1 and 0. I went to my calculator and I put in absolute value of g of x minus f of x so that I have the equation all ready to go. Absolute value is under the math button right here. Okay, so once I'm here, I can go to the table. I can put in at 0, the vertical distance is 0. At 0.43, it is that amount. And at 1, it is that amount. So now we need to go back and look at what the question is asking us for. It says, what is the maximum vertical distance? What is the minimum vertical distance? So our answer is going to be maximum 0.828, and the minimum is 0.8. All right, number 5. So number 5, this is what the situation looks like. We've got this curve, and it looks like so. And it exists just from 1/2 to 8. That's what the problem says. And we want to make ourselves a triangle. So imagine that we pick some random point on here. I don't like that point. I guess it's not as random as I said it was. Right here, let's call that x, comma, y. And we're going to use that point to make a triangle that has as its vertices x comma y and then 1 0 and 5 0. And what we want to do is we want to maximize, is it maximize? We want to maximize the area of this triangle right here. Well, the idea goes like this. An area is always equal to 1/2 the base multiplied by the height. And in the case of this problem, the base is this distance right here, which is just 5 minus 1, so it is 4. And then the height is this distance right here, which is just equal to the y value, which is this thing. So it's 1/2 times 4 times the quantity natural log 2x minus 1/2 x plus 5. So the area is going to simplify to 2 natural log 2x minus x plus 5. That's stage 1. Stage 2, take the derivative. The derivative would be 2 times 1 over 2x times 2 minus 1 plus 0. So the derivative, those are going to cancel, is 2x minus 1. We want to know when that would be 0. That would be 0 when x is equal to 2. Now, does the question ask us, it says, what is the maximum area of such a triangle? So what we need to do next is say, Well, there are three possible candidates. So here's the situation. We know that the maximum is either going to happen at the initial endpoint, at the end endpoint, or at the critical point that we just found in the middle. So we're going to plug all three of those into this equation. Just realized that I made a little boo-boo up here. This should have been a 10, which means that this should also be a 10. I don't think that's going to change the answer one way or the other. Anyway, I put the equation into y1, and then I go to the table. Let's see, delete, delete, delete. We have 0.5, 2, and 8. You can see that the area is going to be biggest right there. So the maximum area of our triangle is this number. Number 7, we are cruising now, and check it out. We've got this semicircle, and we pick some random point on the semicircle, x comma y, and we use that point to make a rectangle. And we want to maximize the area of this rectangle. So we say to ourselves, well, that distance, that's the base of the rectangle. That would be, let's see, x is this distance. So that would be 2, count them, 2 x's, a 1, a 2. And this right here is y. That would be just one y value. So the area is the base times the height, which would just be 2x multiplied by y, where y is this guy. Keep in mind that x has to be smaller than 5 and bigger than 0, because if it was any bigger than 5, then we would be outside of the rectangle, and if it was any smaller than 0, we wouldn't have any area. So there's stage 1. Stage 2 is to get your derivative for a. You're going to have to use, my buddy, the product rule. When you do that, you're going to get 2 times the root plus 2x times 1/2 inside function to the negative half multiplied by negative 2x. That rewrites as 2 times this all over 1 plus cancel, cancel, negative 2x squared. See, it's squared because I got one right there and another one right there. All over radical 25 minus x squared. We want to set this bad boy equal to 0. In order to solve that, we're going to need a common denominator. So multiply by the root here and here. When you do that, you should come up with 50 minus 4x squared, all divided by the root. And we know that this will all be 0 if the numerator is 0. So 50 minus 4x squared equals 0 would mean that x would be equal to the square root of 50 over 4, which is the square root of 25 over 2, which is 5 over roots of 2. I'm going to leave it like that for the moment. Okay, now keep in mind, problem's not asking us for the x, it's asking us for the dimensions. And the dimensions of a rectangle are its base multiplied by its height. Now, we know that the base is 2x values. So I'm going to say that this is 2 times 5 radical 2. And the height would be, let's see, the height is the y value. So I'm going to have to do a little work off to the side. The y value is what we get when we plug this x in. So that would be square root of 25 minus 25 over 2, which is equal to square root of 25 over 2. That sounds familiar. That simplifies to 5 over radical 2. If you're one of these people that likes to rationalize stuff, and I know you do, this would end up being 5 radical 2 by this one would be 5 halves radical 2. That's all you gotta do. Number 8 is almost the same as number 7, so I'm not going to do the whole problem. Exact same idea as the last one. You've got a point, x comma y, and it is on a semicircle, and you're going to use it to generate a rectangle. The one thing that is different on this one is that they didn't tell us the equation of the circle, they just told us the radius. What you're going to do for that is say, well, I know that any circle centered at the origin has an equation that's equal to the square of its x plus the square of its y is equal to the square of its radius. Therefore, x squared plus y squared has to be equal to, that'd be 16 times 2 is 32. So the y would be equal to 32 minus x squared. So that should be enough to get you going. I want you to basically follow the same process you did on number 7, but use a different equation. Number 10 is a classic from back in the day. I did this one when I was in calculus. My father did this when he was in calculus. My father's father graduated from the 10th grade. Here we go. You have bought some fencing, 50 feet of fencing to be specific, and you are going to build a little fence against the house. So you're going to use this fencing on 3 sides to make a rectangle. Incidentally, side note, the fence is to build a nice little monkey pen. We want to maximize the area of this pen. So I'm going to call this side of the pen X and this side of the pen Y. And what we want to maximize is the area, which would be equal to X times Y. Now, we can't take the derivative of X times Y, or at least that wouldn't be very fun. It would have to be implicit. We would really like to have area in terms of just X. So what I'm going to do is add what's called a constraint equation. And the constraint equation goes like this. The fencing is only 50 feet. And so if you take the 2 y sides here and here, and you add to them the x side, you have to get 50. Therefore, y would be equal to 50 minus x divided by 2. And I'm going to grab that, and I am going to plug it in up here for y. But first I'm going to come over here, and I'm going to tickle the monkey. Oh, you're a cute little monkey. You're such a cute little monkey. You're such a cute little monkey. Now I'm going to whoop up right here. The area is x multiplied by 50 minus x over 2. Keep in mind that x has to be greater than 0, and I suppose it has to be smaller than 50, right? You can't have more on this side than the amount of fencing that you got. Okay. So there's stage 1. Stage 2 is going to look like this. Take the derivative of the area. Actually, I'm going to back up. I think it would be easier if we simplified this equation first, right? It's good, just a quadratic equation. So we have 50 over 2 times x, so that's 25x, minus x times negative x over 2, so that's half x squared. I'd also like to note that that right there is facing down quadratic so that we know that when we get our critical point right here, boop, boop, it will be a maximum. So the derivative would be 25 minus x, which means that a prime equals 0 when x is 25. The problem asks us for the dimensions, and so our dimensions will be that x by y. X is 25 feet, and y is then going to have to be 12 and a half feet, because you need 2 of these to get to 50. Please say this is the last one. All right, this time you're making 6 monkey pens, because obviously you have 6 monkeys. You're like the Tiger King, but for monkeys. 1 monkey, 2 monkey, 3 monkey, 4 monkey, 5 monkey, 6 monkey. Anyway, there's a couple different ways you can do this one. I'm going to define x as the length of this pen and y is the width of this pen. And then the area is going to be, well, the area of one of them would be x times y, and then we have 6 of them, so I'm going to multiply that by 6. We also have a constraint, and that constraint is that you only got 2,000 feet of fencing. Scratch that. Sometimes you start a problem and you realize a better way to do it. I'm going to define y as this entire side length and x as this entire side length. Don't worry, each one of these is still for your monkeys, but now the area is just going to be x times y. We don't need the 6 because we changed what the x and the y are. Now we've got a constraint. That constraint looks like this. We've only got 2,000 feet of fencing. Now I count that there are 1, 2, 3 of the x fence lengths. But for the y, there's 1, a 2, a 3, a 4. So there's 4 of those. What we want to do is take this equation, solve it for y, and then plug it in up here. So y would be equal to 2,000 minus 3x divided by 4. I'm going to go ahead and simplify that to 500 minus 0.75x, and then I'm going to zip, 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 zoop it up here, and the area ends up being x multiplied by 500 minus 0.75x. I'm out of room. Whoop. I'm going to simplify that to 500x. By simplify it, I mean you get rid of the parentheses. Distribute. All right, so there we go. I suppose we've got constraints on x here. X is going to have to be at least 0, and it can't be any bigger than, well, we need 3 of them, so it can't be any bigger than the 2,000 divided into 3 equal parts. I don't think that's really going to matter, though. I'm getting sloppy here. I need to finish these problems. All right, so here we go. Stage 2. Take the derivative of this guy. You get 500 minus 1.5x. You set that bad boy equal to 0, and you get that x is 500 divided by 1.5, or in other words, that would be 1,000 over 3. The problem asks us for, does it want the dimensions or the area? It says, what is the maximum possible area of the enclosure? So I'm just going to say this. The area is equal to the x value multiplied by 500 minus 0.75 of 1,000 over 3. And when you get that number, that will be your answer. And that answer is a number. And that number is none other than 83,333 square feet, so that the monkeys can run free. The end.